So, another tool we need in order to really sum up all these ways in which a matrix can be invertible is the notion of the rank of a matrix. All right? So this will be something that you guys will study even more as you go forward in linear algebra. It plays a big role in something called the rank nullity theorem. But we're not quite there yet. We just need the rank as a sort of a number. And what is this number? Well, so for a matrix A, the rank of A, right? The way we're going to define this is the number, the number of leading ones in the row echelon form of A. Right? So of course you can put this into reduced row echelon as well, but we don't need to quite go that far. We just need row echelon. Right? It's the number of leading ones. Right? There's ways you'll learn to define this in the future that will be equivalent, but a little bit easier to compute. Or I shouldn't say easier, but quicker to compute. But what does the rank tell us? Well, it kind of helps us figure out, in a way, how many dimensions the solutions can fill up. All right. So the higher this number is, the lower the dimensions. Which is kind of interesting to kind of think about. But again, you'll study this a bit more. This again relates to what's called the rank nullity theorem. All right. So, what do we get here? Or how do we compute this? Well, let's find a matrix. Now here, we don't need to have a square matrix for this. That's the interesting thing. We don't need a square matrix. So let's look at a matrix like, what's a good one here? I don't want to go too big here. Let's say we have A equals 1, 0, minus 2, 3, 1, negative 6, minus 2, minus 1, and 4, 4, 2, and 8. Okay, so here we have a 3x4 matrix, and let's think for a minute about, what possibilities do we even have for the rank of this matrix? Right? What's the largest amount of leading ones that this could possibly have? What do you think? Well, the largest would be 3, right? Because there's 3 rows, and each row can only have one leading one in it. So, that's that. Right? On the other hand, if we had a matrix with, say, 3 rows but 2 columns only, then what do you think the maximum possible rank of that would be? Well, we could have a leading one in the first column, a leading one in the second column, but then we run out of columns. So there's no more leading ones we could have. So the maximum would be 2. So we'll summarize this again after this example, but the sort of maximum rank we could have is the smaller, if this is an M by N matrix, it would be the smaller of the two. Okay, got a little sidetracked there. So let's compute the rank of A. Okay. Now, when we're computing the rank of A, we just need to put this into row echelon form. And let's go ahead and do that. So, if we're going to put this into row echelon form, where should we start? Well, we have this 1, right? We have this 0. We need to turn this -2 into a 0. So here we would do row 3 plus 2 row 1 goes to row 3. Right? If we do that, so 1, 3, minus 2 and 4. 0, 1, minus 1 and 2. And then, so plus 2 times row 1, so this actually is 0. This is also 0. This is also 0. And this happens to be 16, actually. Now, one thing I want to point out here is this right here is not a system of equations. Like, this is not the augmented matrix of a system of equations. This is just some 3x4 matrix. Right? I want to bring that up because normally this kind of thing here would signal no solution. Right? But again, this matrix here would be like just the left side of the equations. Anyway, so back to where we were. So now that we've done this, we have this leading one and zeros below it. And coincidentally, we actually already have another leading one here and zeros below it. So that's great. Now there is no leading one in this third column. There's no way to get one. So we ignore that column and go on to the next one. So we need to make this into a leading one. Right? Now, of course, we could, just say, well, obviously we can make this into a leading one, but let's go ahead and do it just to be thorough. Right? All right, so let's. Right, so we'd get that. So how many leading ones do we have here? Well, we have 1, 2, 3. Right? So this would be an example of a matrix where the rank, we could say rank of A. This is our usual notation for the rank. In this case, it's 3. Okay? And this is an example of what we would call max rank or full rank. Okay? And again, I wanted to, we mentioned this before the example here, but I want to re-emphasize here. I want to give you this definition. So an M by N matrix A has what we call full rank if the rank of A, this notation might look a little funny here, but it's the minimum of M and N. All right, so sorry about that. So what does that mean? Right, what is this min mn thing? All this notation here means, this means sort of like the smaller of M and N. right? So just whatever number is smaller. So if it's a 3x4 matrix like we had, then the full rank would be 3. If it's a, say, 6x3 matrix, then, or let me say 6x4 matrix, then the max rank would be 4, because the smaller of the two numbers, 6 and 4, is 4. Right? That's how max rank works, or full rank works. Right? Full rank is just basically what this translates to in kind of more plain terms is sort of as many leading ones as possible. Right? So if you reduce this matrix to row echelon form, sort of every row possible has a maximum 1, or every column possible. Right? It has the highest amount of leading ones as the shape of the matrix allows. Right? So we'll talk in the next set of lectures about how this kind of relates to the invertibility of a matrix. Right? But it turns out that just by computing this simple number about a matrix, we can say quite a lot about it, actually. Which is pretty interesting. We can say quite a bit. So yeah, so we'll talk more about that in the next video.